I mean, historically, what people saw, Lyman in 1906 looked at the spectra of hydrogen in plasma tubes and saw there was a Lyman alpha series, right? And there was the Lyman alpha series, and Rydberg came up with this empirical formula, which said something about that the energies of the wavelengths in the Lyman alpha series was dependent. They were given by some numbers n, and there was some constant that we now call the Rydberg constant. It's like it's related to this Rydberg with h bars and c times 1 over lambda squared 1 minus n squared. That was an empirical formula. And what it corresponds to are all the p to s transitions. You just calculate them, right? Where, I'm sorry, it's not over lambda squared. This is over lambda, right? This is h bar nu. So this, Rydberg constant here is just hc. The other way, this is the energy divided by.
And it's from P to S because of the selection.
That's right. Now they didn't know that, but Bohr, of course, wanted to explain this discrete set of lines and came up with the Bohr atom, right? In order to describe this, and it was through the Bohr atom that de Broglie said we can explain Bohr's model in terms of, well, there's, waves that have to fit around these orbits, and then there was Schrodinger. So it's, there's a wave mechanics and quantum mechanics didn't come out of nowhere. There's empirical, it's physics. We do empirical work, and then we try to fit and explain models that connect to those things. Yeah?
I'm sure you have the units right for that.
Let's see. Let me get this right. So, energy is h nu, which is hc over lambda. This is what I'm calling the Rydberg, and this is, right. So I want it the other way around, don't I? So that I have to divide, this is over lambda, Rydberg over lambda. Energy, no, actually I had it right. Divide by hc, and then I get this constant, correct. So the point here is that the thing I want to emphasize on this is the idea that, there are empirical studies that open up all new theoretical areas. We're in a period of that, in my opinion, right now, in cosmology. What the heck is going on? What is this dark matter and dark energy junk? What the heck is this? We don't know. And we sure hope that this is, I feel this is the century for gravity. You guys need to be thinking about that. This is some of the big open questions in fundamental physics, in my opinion. Now, one of the things we're going to study in more detail that's also important that led to a big new understanding in the nature of fundamental physics is spin. Spin itself also was, although we were taught about it in the context of the Sturm-Gerlach experiment, in fact, the Sturm-Gerlach experiment was done, but no one really paid much attention to it and didn't really think about why they saw 2 lines rather than 1 or 3 for the fact that angular momentum should have had an integer value and should have had 2L plus 1, so it should have been an odd number of lines, and you had an even number of lines. It was through the spectrum of hydrogen and the fine structure of hydrogen that the whole notion of spin really was understood. That's really historically what happened. And we'll come and talk about that in just a little bit. And how are we going to do that? So what we want to talk about today is trying to solve the Schrödinger equation, particularly the bound states, the stationary states of atoms, molecules, what have you, when we can't solve the problem exactly. There are very few problems that we can solve exactly. You can name them, right? The harmonic oscillator in 1, 2, 3 directions. We could solve the hydrogen atom non-relativistically in Schrödinger equation. And basically, a whole bunch of potentials where the nature of the potential is some power of R, so that this is some, instead of the Laguerre polynomial, we have some other confluent hypergeometric function where we use the same kind of power series solution. So, you know, there's the Paschen-Teller potential, and there's a few other potentials we could solve. But basically, that's it. So, in general, we want to solve problems. In physics, the art is the art of approximations. How do you do good you don't have exact solutions, but you want to find approximate solutions, and you want to have them be controlled approximations, so you know exactly how this converges, okay? So in order to do that, we're going to look at situations where, and this is quite typical, where we can have the notion of a perturbation. Okay? So, for example, the case that I was just discussing, relativistic corrections to hydrogen. So as I discussed when we first introduced the hydrogen atom last week, what I said was, well, we're going to just look at the electrostatic force between the proton and the electron, and ignore any magnetic forces that would come into fact. The electron is moving relative to the proton, and there's a velocity, and therefore a magnetic field, a current, and that should be a term in the Hamiltonian, which we just ignored, okay? There are other relativistic corrections. The kinetic energy is not just p squared over 2m, but there's corrections to the fact that there is energy in the mass, mc squared, right? So there's a relativistic kinetic energy. So there are all terms in hydrogen that have to do with, that are on the order of, that are small. There's a small parameter here. And that small parameter is something about the speed of the electron relative to the proton compared to the speed of light. If that's small, then the relativistic corrections are perturbations to the problem, right? Now, we did this, you just did this in your homework, and found that in atomic physics, the characteristic speed of the electron in units of C is what? You just handed that homework in.
37.
Yeah, it's the fine structure constant. E squared over h bar c, okay? Which is about, everyone knows, 1 over 137. And that's smallish, you know, pretty small, less than 0.01. So that's a small parameter. It's not nothing. It's measurable stuff, but it's small. And what find therefore, we'll see that the to lowest order in powers of alpha, the Hamiltonian for hydrogen, you know, we have the standard Hamiltonian. Yeah.
I'm just basically extrapolating on this idea in elements other than hydrogen. E squared can be viewed as Z1, Z2.
Uh-huh.
So it turns out that as you get to higher elements,
It's a good
the parameter approaches 1.
It doesn't get that big, but it gets much bigger. So you are absolutely correct. In bigger Z atoms, relativistic effects become more important. Absolutely. Because they're moving much faster. We'll come back to that a little bit. But, so they'll continue the sort of thought that, the line of thought that I was going through over here. So this is the Hamiltonian, and then there are correction terms, and we'll find that they're proportional to alpha squared. And there's things like p squared over the 8 times the mass, and then a half the coupling of the orbital angular momentum of the electron to its spin. There's a spin orbit coupling. And then this is all in units of the atomic units. Okay?
Why is alpha squared?
Well, this, I mean, you'll see this. This is clear because this depends on the momentum squared. This, we'll come to that. We'll come to that. All right. So, hold on a moment. Let me bring up what I wanted to bring up here. All right. Yeah. I know I was missing something, and that's what I missed. So this is what we might call the zeroth order Hamiltonian. The Hamiltonian in the absence of the relativistic corrections. And then there's a Hamiltonian that is proportional to a small parameter here, okay? I might leave that small parameter outside here, call this thing H1, and this, you know, alpha squared times H1. So that this is small, obviously small compared to that. All right? The energy scale of this is on the order of the Hartree, and the energy scale of this is alpha squared times Hartree. So this is a small perturbation relative to this. And there are many situations that we deal with in physics that are like this. There is a dominant effect. We might know how to solve that dominant effect exactly, or pretty, even, you know, maybe some approximations there too. And then we have some correction terms, okay? So what we want to do now is look at how we can approximately solve the Schrödinger equation in situations like this. All right? So what we're talking about now is what's called time-independent perturbation theory. All right? And what do I mean by that? So we have our Schrödinger equation that we want to solve. And what we're going to say is that the Hamiltonian can be decomposed in the same way. There's some H0, which I know how to solve, and then there's some H1, which is small in the same sense compared to H1 in terms of the energy scales associated with it. And the way we typically do that is we put a little constant lambda as a kind of bookkeeping. So I think of h as a function of this parameter. When lambda is 0, it's h0. And then lambda is some continuous parameter that it's just there in order to let us do a power series expansion in a convergent way. All right? So we can think about, in this case, lambda is alpha squared, for example. All right, so this is our Hamiltonian, and we're looking for stationary states. Those stationary states will depend on this value of lambda, and the energies depend on that as well. Right now, as I say, it's just a bookkeeping parameter. Right. Okay. So we want to do a Taylor series expansion of this equation in powers of lambda. Okay. Now, what we're looking at here is bound states. Okay. This perturbation theory is applied at this point only to the discrete part of the spectrum. This n is not necessarily the principal quantum number, but it could be. It's just some label here for the bound states, and it could be a set of quantum numbers. But these are just bound states of the system. That's all we're looking at the moment. All right? So, with that said, what we do is the following. We say, let us say that the solution to this problem can be expanded in powers of lambda. Sorry. Yeah, lambda to the power k, and then I have un the k correction to that. Okay. So this is an ansatz, we're saying, that we can expand this as a function of lambda. Okay.
Is that the base of the original eigenstates of H0?
So this is not necessarily a basis of any kind. These are basis states. They are the eigenstates of the full Hamiltonian. Okay? Those kets in Hilbert space, I'm saying, are continuous functions of lambda, and I can write therefore a power series solution. Okay? Where these are vectors in Hilbert space. They're just other vectors in Hilbert space. They're not a basis.
They're not necessarily in the same Hilbert space?
They're in the same Hilbert space.
They're all in the same Hilbert space.
They're in the same Hilbert space. This is just a relationship between vectors. They're all in the Hilbert space.
Okay.
But let me emphasize one point. I'm about to do that. These are not necessarily normalized kets. They're not states. This is a mathematical statement. I have a vector in Hilbert space. That vector in Hilbert space is a function of some parameter. This is a label, right? And now I'm just doing the Taylor series expansion. Now, we can always think about this. So I can look at this as there's the zeroth order solution and a difference between that and that, okay? Where this is everything, the sum, everything from k equals 1 to infinity, all right? Now, the way I've written this is not normalized. Okay? So what I'm saying here, and of course then I renormalize at the end of the day, is think about it as a vector. Here's the vector, the zeroth order solution. So these are eigenvectors of H naught. So we solved those problems. Those are the hydrogen atom in the non-relativistic approximation, for example. Okay? So that's some vector in Hilbert space. Now, the perturbation, it doesn't matter what it does along this direction. That just is, we would just renormalize it. All I care about is how the perturbation changes things perpendicular. And then I have, so this is how the perturbation affects the state perpendicular to it. How it changes it along the state is irrelevant. That just gets renormalized. All I care about is how it changes. Then the true state would just be, I'd renormalize it. So what I care about is how does the perturbation change the eigenstate along the direction perpendicular to it. Okay? So,
So delta UN is orthogonal actually.
exactly. Let me put the ket inside, and I was about to say that. So this delta UN is orthogonal to U dot.
I'm sorry, what? I didn't catch what Amira said?
He said, so it's orthogonal.
Oh, okay.
And that's, yeah.
Thanks.
Yeah. Now notice these guys, I'm not saying anything about their orthogonality to one another or anything like that. I mean, generally speaking, the first, for two different Ks, this is not zero. These are not orthogonal. I made no claim of that sort. All right. In addition, the energy eigenvalue is a continuous function of lambda, and it can be expanded in a power series in lambda as well. All right? Yeah.
And just to clarify the last statement about the orthogonality.
Uh-huh.
So you're saying that if you take the k equals 0, say with all others, you get 0. But if you take it with only individual k's, then those individual k's don't add up to 0, don't equal 0. So like u of n of 1 and u of n of 0 won't equal 0.
So what I'm saying here is that when k is not equal to k prime, okay? So I'm expanding my vector in this power series. These different pieces in that power series, I'm saying nothing about them. They might be there, they might not. There's no demand that the different, this came back to some question of whether I should think about each one of these as a separate basis for the Hilbert space. They're not. It's just the expansion. Okay? The vector, the total vector, UN, forms a basis. Okay? But the pieces in the sum are not the basis. All right? All right, so with that said, now what we can do is take these two expansions, these two ansatz for the state and the eigenvalue, and plug it into the Schrödinger equation. So what that tells me, so h of lambda on un is En of lambda on un of lambda, implies that H0 plus lambda H1, that's my Hamiltonian, acting on the sum, k equals 0 to infinity, lambda to the power k, u and k of lambda is equal to some dnk of lambda times k prime, lambda k prime, u n k prime. Okay, just plugging it into those.
Is there lambda dependence in H1 or the use of n?
Sorry, there is no lambda here. That's incorrect. Pardon me, thanks. This is the function. That's the only lambda dependence.
The use of n?
But they do not. Yes, thank you. That's all messed up. Okay. These are not lambda dependent. I factored. That's what we did. We the power series. Thanks. All right. So now, given this expansion, we can just collect terms, the different powers of lambda, right? Because it's a continuous function of lambda, each term must individually be equal. So we can look at the 0th order term. K equals 0. Well, the only terms there, that's what we had already written down. This is the solutions that we assume that we know. Okay? Those are the terms that have no powers in lambda. Now let's collect the 1st order term. So that would be equal to K0 times UN, the 1st order piece, plus H1 acting on the 0th order piece. Both of those are 1st order. And then I have a EN0 UN1 and an EN1 UN0. Okay. Those are, on the left-hand side, the terms that have 1 power of lambda. And on the right-hand side, the terms that have 1 power of lambda. All right? And now we can solve for the 1st order correction to the energy eigenvalue and the 1st order correction to how the state changes. How do we do that? Well, what I can do is take this and project it onto UN0. Okay? So that is equal to that. Okay. Now we have the following relations. There's a couple of different ways you can look at this. This is an eigenvector of H0. This is a Hermitian operator. Therefore, this is equal to the eigenvalue En0. Okay? And so this term cancels with this term. Okay? This, the original states we take to be normalized. So this is 1. And thus we have solved for the 1st order correction to the energy. To lowest order, if I want to find out how the energy eigenvalue shifts in the presence of the perturbation, I just look at the expected value of the perturbation in that state. Okay? So for example, come back over here. If I wanted to find out what the first order, I have to be a little bit careful what to think about. There's some subtleties here. But I might be able to just say, well, if I want to find out how the ground state of hydrogen shifts in the presence of these relativistic effects, I just take the expectation value of this in the ground state. And that gives me, right? Because we know that the ground state, we expect if we have the ground state, then this is the energy of the ground state, right? And so there's a piece that comes from the 0th order and then a perturbation. Okay? So this is the simplest, most fundamental equation in perturbation theory. All right, very good. Now what about the first order correction to the state? How do I find that? Well, the way we go about it is to use the fact that the original eigenstates of the 0th order Hamiltonian form a basis. So my set of 0th order eigenkets form a basis. All right. So that means that whatever this vector is, it itself forms a expansion in the 0th order eigenvector. Yes, Stephen.
I think I'm missing a term here. When you solve for the first order energy correction, you seem to only have the H1 component. Does H0 go away?
This term was equal to this term on the right, and they cancel.
Oh.
Yeah.
So in that expansion, you assume that the nth component doesn't
This should be over m, sorry.
appear.
That's because of this
So
condition.
would it say that this overlap over there, I mean, regardless whether it's cancelled or not, is 0?
It would be. Both but in that case, it would be 0 irregardless, right? Even if this wasn't equal to that, they're both 0.
Yeah, just to make sure.
It's true. That's true. This is 0 anyway.
Yeah.
It also cancels. We didn't make that choice. But the fact that I say n is not equal to m is because of that assumption we made that we're only going to look at the piece of the perturbation that is orthogonal to U0. Okay? So, right. So now we can look at this. Let's take this equation, again, this one over here, and instead of taking the inner product with the state with the same n, let's take the inner product with the state m not equal to n. Okay, let's do that. So what do we get? So for m not equal to n, u m n, no, u and n. What are we doing? Yeah, u0, h0, psi n un1 plus um0 h1 un0 equals en0 un0 un1 plus en1 un2. 0, u, or u. Okay. So, firstly, these are orthogonal. The 0th order ones are 0. By the same argument, this is 0 or this cancels this. Both are true, right? Okay, good.
They're not cancelled because this is EM0, no?
No,
H
oh yeah, that's important, sure. Yeah, that's truly, never mind, thank you. Yeah, that would have screwed the whole thing up. So let me go back. UN0. So H0 on this is UN. So that's EN.
Shouldn't that be a
no, no.
Shouldn't that be a 1?
Yeah, no. It's UN1.
The superscript on the.
Where did I, okay, thank you. All right, let's do again. This acts on this, that's EM. So now I have EM0.
Yeah.
Right, so, okay, that's all good.
Yeah.
And this is what we called, according to what we wrote somewhere, CM1. It is the expansion of the UNs in that basis. That's what this is, right? And that's the same thing over here. So now we can combine these terms. And what we get is the following. EN, M as in Mary, minus EN as in Nancy, times this expansion coefficient is equal to minus UN0, H1, UN0.
Should the C have a second index?
Or is it just the 1?
No, it's this.
Yeah, but isn't it different for each nth vector?
I'm talking about this, it's true, this is for that n. Indeed, it is for, I could keep that in. It is for that n. But it's just that index, it's just this one that I'm solving. Back to that, but you're right. It is for that n. We can solve it. And find that this is equal to this off-diagonal matrix element. So what we find here is that to first order, the eigenvector is the 0th order plus a sum over m not equal to n u n 0 h1 u n 0 bless you over en minus en. Of course, unnormalized. The full state, we have to then renormalize it. Now here's a few very important points. What we notice here is that the effect of the perturbation is to take whatever was the original eigenstate of Hamiltonian and mix in. It's not a mix in the statistical sense. We say the term mix, it really means superpose in, coherently mix in other eigenstates into the problem, so that we don't have, if this was, say, pure S state, you might have a little bit of P state mixed in. And that superposition depends on how much of the other eigenstates now get mixed in. Depends on the off-diagonal matrix element of the perturbation relative to the energy difference of those two. Okay? So there's something else you notice. We assumed this was small. But if En is too close to Em, then this don't work. So firstly, this whole procedure, it breaks down if there are degeneracies. Yeah.
You say it breaks down if it has degeneracies, but then you also mentioned that even if it was close.
That's right. So it's got to be, it breaks down if it's too close to degenerate. Even if you have states that are very, very close to one another, and then you put on a big perturbation, this numerator is huge compared to that. And that would mean this doesn't converge. We're going to talk about degenerate perturbation theory and near degenerate perturbation theory. Okay? So this is the whole story in perturbation theory. How big is the coupling between neighboring states or some states, energy levels that are separated? How big is the coupling induced by the perturbing Hamiltonian compared to this energy scale?
I guess lambda is missing somewhere, right? In UN.
I mean, we've already factored out.
In UN, in the state itself.
Right. I mean, in some sense, this is this. If I wanted to put that in, this is first order in lambda.
Yeah.
Right? But that is all really this. This is, in some sense, playing the role of lambda.
But lambda would make it really small, right? Lambda,
We assumed it was, but it might not be.
In this case, lambda is 1 over alpha squared, right?
No, I'm not. This case is general. It's not the fine structure Hamiltonian. It's not anything specific. It's a Hamiltonian that we assumed had this form. Yep.
So if I'm understanding this right, though, we can't use this at all with the hydrogen atom, right?
That's right.
Okay,
We'll come back to that.
okay.
Yep.
Would going to second order perturbation give help alleviate this problem?
No, I mean, it just doesn't converge. Because then the next, I mean, you want this to be a small parameter. And if it's not, well, then second order is even bigger. Okay, so we have to do something different. We'll come back to that probably next week. But let us talk about second order. It might be the case that this vanishes. So let's go back over here. We said that the first order correction to the energy was given by the expected value of H1 in the state that we want to see how the energy shifts in the presence of the perturbation. But what if this is 0? Well, then we have to go to second order to see the lowest non-vanishing correction. Okay, so let's do that. So to second order. I have H0 times the second order piece plus H1 times the first order piece, okay, equals En0 times the second order piece plus En1 times the first order piece plus En2 times the zeroth order piece. Okay. So these are all the terms that had lambda squared. Okay. So once again, what I will do is take the inner product of this with the zeroth order with the same n. That's how we get these guys. So once again, we took this to be orthogonal to this. So that's 0. This is orthogonal to that. That's 0. We do the same trick here. This is En0 times Un0, Un2. So that's 0. And thus, we have the following expression. And the second order correction to the energy is equal to Un0 times that operator acting on Un1. Okay? But we know what Un1 is. Here it is. This is the first order piece in the correction. So now we can plug that in. That is thus equal to the sum m not equal to n of Un0 H1 Un. Sorry. Yeah, sorry. Okay. Let me do this again. So I'm going to plug in. I got Un0. I have H1, and then I have to act that on that state. That's Um0, Um0, H1, Un0 divided by En0 minus En0. That is correct. Or, as it's most typically written, the sum over m not equal to n, the off-diagonal matrix element squared n squared divided by En 0 minus E0.
Shouldn't the bottom be square as well?
No. I just plugged in one, I just take that U over there, that U1 on that board, and plug it in. That's what I did. Of course, this has the right units, because the numerator is energy squared, and the denominator is 1 power of energy. So this is the second order correction that depends now on the off-diagonal matrix elements. The first order energy correction depended on the diagonal matrix elements of the perturbing Hamiltonian. The second order corrections to energy depend on the off-diagonal correction, off-diagonal matrix elements. It depends on the square of this off-diagonal matrix element of this. Again, should be small. If there are degeneracies, you're screwed. Okay, at least using this method. Okay, now I just want to emphasize a few points here. If we go back to what we're doing here, we've developed a method here, we explained the method here, that is really for how you approximately diagonalize a matrix. I mean, if we're thinking about it this way, I have H, I want to find the eigenvalues of a matrix, right? Forget about the eigenvectors for a moment. I want to find the eigenvalues of this matrix H. This matrix H itself is a sum of two matrices. Okay? And this procedure tells you, you have some H0 in the basis of U0, which are, has only diagonal terms. And then you have some matrix H1, which has, whatever, it has some matrix elements somewhere. And we're showing how the eigenvalues of this total matrix change in terms of matrix elements of this perturbing matrix. You just, to get the first order correction, you just add the diagonal elements to these, and that gives you the first order correction to the eigenvalues. And then the second order corrections depend something on the off diagonal elements of this thing compared to the energy differences between them through this formula. Okay, so that's a math perspective on this. But there's also, I want to talk a little bit about the physical perspective on perturbation here. Particularly, let's think about second order perturbation theory. Intuition, physical intuition. On the second order. So let's consider the situation where, for example, to first order, the expectation value, that's not even so important. Let's just suppose that for some state, the first order energy vanishes. So this is the first order correction to the energy shift. Okay, let's just suppose that were true. Now, it might be the case, and it often is the case, that even if the first order, the state itself is perturbed. So we have what we've written over there is that there is a u to first order is un0 plus, I'll put those down equals 1 in this case, un1. Right? With lambda. So that could be true, even though the energy shift to first order is 0, the state itself is perturbed to first order. And that piece need not vanish, because that piece depends on the off-diagonal matrix element, which could be non-zero, and often is. So now I can think about what is the second order correction is that to first order I perturb the Hamiltonian, and then now that first order state has a shift in the presence of the perturbation. So what I would say is then that the energy is always given by this. That is always true. This is the energy eigenvalue, right? Now I can expand this to different orders. Notice I was careful to keep the normalization here because the UNs, other than UN0, are not normalized. Okay? So now if I keep terms here to, let's say, this is UN0 plus lambda UN. It's icky. Let me try to be more clear with 0. H0 plus lambda. Oops. Ew.
This gets clean now, at least.
At least there's that. All right, lambda un1 times h0 plus lambda h1 un0 plus lambda un1 divided by un1 plus lambda un1 times un0 plus lambda un1. Okay? So now I can collect right on this side. This is equal to en0 plus lambda en1 plus lambda squared en2 plus dot dot dot. Okay? It's just another way to do this perturbation theory. And what I see here, so the denominator here is going to be to second order in lambda. There is a 1 plus lambda squared un1 times un1, right? That's this term. These guys are orthogonal. We've said the un, this should be un0, pardon me. This is orthogonal So this, etc. And then I have terms up top. I have terms that are En0. I have lambda En1. And then I have other terms. I have terms that are of order lambda squared here. Let me get my notes here because I'm going to screw it up and I lost it.
Over there.
Thank you. Right. So then I have lambda squared times UN1 H0 UN1 plus, hold on a second, that doesn't look right. H0. Yeah, I do have a term that looks like that. That's correct. And then I have a UN1 H1 UN0 plus UN0 H1 UN1. So now I have to do a Taylor series expansion on the denominator in order to get a power series that's just a power series in lambda squared. And when I do that, I get the following. That this whole thing equals En0 plus lambda En1 plus lambda squared times UN1 H1 UN0 plus UN0 H1 UN1 plus UN1 this should be H. H0 is H1 minus En0 UN1 That's right, because that just comes from taking that denominator and bringing it up. And then I get a lambda squared times that with a minus sign. Because 1 over 1 plus alpha, or A, is approximately 1 minus A for A small. Okay? So this term cancels that term. And I get an expression here that messed up something.
The UN1, you know, you have UN1 on H0. Shouldn't be UN0 according to...
Jeb. Let me just,
the first term.
let me look at this here.
Then or should have
2 in each one.
I have this term is this, and this term is this. This term is this.
Not,
You have UN 0, so you have 1.
yeah.
Oh, yeah, that's right. So this is UN 1.
Yeah.
Okay. Right. Right.
And that cancels with the one below it, not the one on top. So E and 0 cancel with the one relative to its left.
I'm sorry, my algebra is messed up here, so I'm gonna have to fix this next time, because it's just, there's something missing. I'll fix this next time. But let me skip the algebra. I'll correct it next time, because I think it's wrong in my notes, and that's what screwed me up. But let me just emphasize the main physics point here, which is that each order of perturbation theory can be thought about in this way, okay? So to 0th order, I just have the expected value of the Hamiltonian to 0th order. That perturbation can also change the state. Now that perturbed state has a new energy. So now I look at the expectation value of the perturbed state with respect to the Hamiltonian, and there's going to be then a next order term, because there is an H1 interacting with the perturbed piece. So if I had a first order perturbation interacting with the H1, that gives me E2, etc., etc. We will see an example of that next week when we look at, for example, the problem of the polarizability of an atom. That is to say, we have an atom, and say we put it in an electric field. That electric field, to 0th order, if it's spherically symmetric, doesn't have any energy shift. But to 1st order, I perturb it, and I stretch the electron relative to the proton, and create an induced dipole moment. And that induced dipole moment then interacts with the field. That gives me a 2nd order. That's what we would call the quadratic Stark effect. So we will pick that up next time. Yeah?
So just real quick, I mean, you were saying, suppose that the E sub atom 1 is 0. You just said that just as a motivation to explore the
Yeah.
because in reality, that would be very unlikely, right?
No, it could be extremely likely.
Well, okay, I don't understand that because, okay, so UN of 0 is the eigenstate of H0, is that
Yeah.
correct?
Mhm.
So I thought that H1, the effect on that would be small. I would think that H1 acting on that would not rotate it orthogonal to itself.
So this is not a rotation,
Well,
okay? So you shouldn't think about it that way.
Okay.
It's really a question of what are the symmetries of this relative to that. So for example, the example I just gave you. Suppose, and you'll see, you should have seen this in your homework. Or maybe it's the next homework, the one that's coming, the one that you're doing right now. Suppose H1 was proportional to Z. So I apply an electric field in some direction. Let me call that direction Z. Now I look at what is the expected value of that in the ground state of hydrogen. It's 0. No matter what the coefficient is. Even though this is a tiny, it could be that there's some lambda outside here which is tiny. Whether or not this is 0 depends on the symmetries of that Hamiltonian relative to that state.
So it's not that H1 is the effect of H1 small, it's the lambda out front that will that reduces.
That's right.
Okay.
Now, as we said, if we come back to this expression, I can combine this. So the effective lambda here, the thing that allows this is alpha squared. So this is part of H1.
Right.
But it still could be the case, even if that's true, even if I absorb alpha into the whole thing, that the expected value of this in some state of H0 is 0.
Okay.
Just because of symmetry.
Yeah, because now I'm thinking about it, that H1 isn't very small in some ways.
It is small. This is 27.2
Oh, well, I mean,
electron volts. This alpha squared multiplies it and makes this whole term tiny. 10 to the minus 4 smaller than this term.
Well, I mean, yeah, but I mean, disregarding the
Right.
constants on the sign,
Yeah.
the operators in the middle could have a big effect.
That's
on this.
right.
Okay.
That's right.
Okay.
But in the end, it's all about symmetry. So the reason that this vanishes for the case that I just described is that I have a spherically symmetric s orbital. And then I apply an electric field in some direction. And the mean value of that is 0 because the orbital is spherically symmetric, but it doesn't matter, it doesn't have an average. The average z is 0. So the dipole moment of the hydrogen atom is 0, period. Until you perturb it, you make an induced dipole. Now that induced dipole interacts with the electric field, and that makes an energy shift. And that's a second order effect.
Okay.
But the first order, it does nothing. All right, sorry about that, folks. Every once in a while, I'll screw me up. I will fix that.